All right, today we're diving into something that sounds like it's straight out of a sci-fi movie, but it's very, very real. Zero-knowledge proofs. This is an idea that's totally shaking up how we think about privacy and security in our digital lives.
So let's kick things off with a question that sounds kind of impossible, right? How can you prove you know a secret, like a password or a private key, without actually telling anyone what it is? This is the exact puzzle that zero-knowledge proofs, or ZKPs, were born to solve.
To really get our heads around this, we're going to skip all the heavy math for a second. Instead, we're going to use a famous story that just perfectly illustrates the core idea behind all of this. So picture this, a cave shaped like a ring. Inside, there's a magic door that blocks the path, and you need a secret password to open it. Our prover, let's call her Peggy, says she knows the password. Our verifier, Victor, isn't so sure. So Peggy goes into the cave down one of two paths, A or B. Victor can't see which one she took. Then, Victor walks to the entrance and yells out a random challenge. Come out of path A. Now, if Peggy really knows the password, this is easy. She just opens the magic door if she has to and walks out of path A. Of course, doing it once could just be luck, a 50-50 shot. But what if they do this 20 times? The odds of her just guessing right every single time are less than 1 in a million. At that point, Victor is totally convinced. Peggy proved she knows the secret, but she never, ever said the password out loud. And there you have it. That little story, it's the perfect way to understand the formal definition of a zero-knowledge proof. It is a method, a protocol, that lets one person prove to another that something is true without revealing anything else. The verifier learns nothing except for the fact that yes, the statement is true. That's it.
Okay, so for something to actually be a zero-knowledge proof, it can't just be a clever trick. It has to follow 3 really strict rules. These aren't guidelines, they're the absolute foundation that gives ZKPs all their power. So let's break them down.
And these are the 3 pillars we're talking about: completeness, soundness, and of course, the zero-knowledge property itself. Each one of these is absolutely critical for the whole thing to work.
First, you've got completeness. And this one's pretty simple, actually. It just means that if the prover is telling the truth, if they really know the secret, the proof will work, every time. An honest Peggy will always pass Victor's test. The system just works the way it's supposed to.
Then there's soundness. And this is all about making the system cheat-proof. It means that a liar, someone who doesn't know the secret, has almost 0 chance of fooling the verifier. A fake Peggy who's just guessing will get caught because the odds will catch up to her really, really fast. The proof is secure.
And last but definitely not least, we have the magic ingredient itself, zero-knowledge. This is the big one. It guarantees that the verifier learns absolutely nothing new about the secret itself. Victor walks away 100% sure that Peggy knows the password, but he has no idea what that password is. The secret stays secret.
All right, so we've got the rules down. But, in the real world, things are never that simple. ZKPs come in different flavors, and they all have their own pros and cons. The 2 big ones you're going to hear about are ZK snarks and ZK starks. Understanding the difference is super important.
So let's break down the 2 main types. Think of it as a trade-off. On one hand, you have ZK snarks. The S stands for succinct, meaning the proofs they generate are tiny, just a few hundred bytes, and they're incredibly fast to verify. But here's the catch. They require what's called a trusted setup. It's a special ceremony to create the initial parameters, and if that gets compromised, the whole system is vulnerable. On the other hand, you have ZK starks. The T stands for transparent. They don't need that risky setup at all. They're also considered resistant to attacks from quantum computers, which is a huge deal for future-proofing. The downside, the proofs are a lot bigger. So you're choosing between small and fast with a bit of risk, or bigger and a little slower but more transparent and secure.
So this is all really cool theory, right? But what about the real world? Where are we actually using this stuff? Because this is the point where ZKPs go from being a neat academic concept to a technology that's changing everything. And the answer is pretty much everywhere. The applications are just exploding. You can have truly anonymous voting systems. You can prove you're eligible for a mortgage without having to show the bank your entire spending history. On the blockchain, this is a total game changer for scaling. You can bundle thousands of transactions into one tiny proof. It's also being used to secure everything from global supply chains to the smart devices in your own home.
And we're not talking about small changes here. The stakes are massive. I mean, just take voting, for example. The problems with our current systems, the long lines, the security concerns, they're estimated to cost over $1 billion in lost productivity. ZKPs can make voting secure, private, and way more efficient. But it's not just about privacy. ZKPs have this other superpower, making systems way more efficient. There's this really clever technique called commit and prove, and it basically slashes the amount of memory you need for huge calculations. Now, it's a bit technical, but the idea is a game changer for building powerful apps that can run on even small devices. Okay, so how does this actually work? Well, normally a computer has to hang on to every single piece of data while it's doing a big calculation. With commit and prove, it can use a piece of data, prove it was used correctly, and then immediately forget it, freeing up memory. You can see it right here in the table. After each step, the system just drops the info it doesn't need anymore. It's like cleaning your desk as you work instead of waiting until the end. This memory recycling means you can run massive computations on hardware that just couldn't handle it before.
So what's the big picture here? Where is all of this technology headed? Well, it's pretty clear that zero-knowledge proofs are way more than just a theory now. They are fast becoming one of the fundamental building blocks for the entire next generation of the internet.
And look, this isn't some niche, futuristic idea. You've got people like Ethereum's founder, Vitalik Buterin, saying that ZK rollups are absolutely essential to get blockchain networks to the scale they need, to handle hundreds of thousands of transactions a second. This isn't just a nice to have, it's the key that could unlock global adoption. Which really leaves us with this incredible, mind-bending idea. Think about it. For basically the entire history of computing, to prove something was true, you had to show your data. ZKPs completely break that link. They separate the proof from the data. So I'll leave you with this thought. If we can now verify almost anything without revealing the information behind it, what part of our digital world won't that change? The possibilities are honestly staggering.